Today's another pretty fun-filled day of trying to understand what these graphs can do. I plan on going over the homework in some more detail, and even this warm-up has something to say to us. Maybe you can hear it already. It's saying to us, +7. But seriously, I want to see if you can sort out what might be the same, what might be different from yesterday. And again, there's definitely a number that's being added to the end. Now, if you're saying, well, what should I do? Well, see if you can find the vertical asymptote. See if you can find the horizontal asymptote. See if you can find the x and y intercepts. Get into it a little bit, and then don't be scared to look at it on your calculator. I kind of want you to see if you can figure out what happens, particularly with that +7. If you have your homework, that's a good idea. I'm not checking it. That doesn't mean it's not important. But if you have it handy, we'll get to that also. When you do this, you want to try to use the sort of pencil and paper techniques. That is, working with the number 0 as appropriate. But eventually you do want to go to your calculator and you want to see what it shows. Do you have to change an answer? Or you're not sure how to get an answer? Again, the calculator can shed a little light. Hoping that you're taking the main idea from yesterday. I mean, at least one of the main ideas. If the denominator is equal to 0, you got a problem. Okay, so what number makes the denominator equal 0? It's a fraction. It's no big deal. It's just x equals 1/3. That's going to be a vertical asymptote, honestly, because it's not a whole. We'll sort of get back to the whole thing in a few days. I'm going to skip the horizontal asymptote. Did you think about the y-intercept? Again, a y-intercept is a pretty standard mathematical idea. Even if I had not taught you anything yesterday and you did what you have always done with the y-intercept, you should be able to plug in a 0 for x. If you plug a 0 in for x, and as I try to say here, trust the math that you've already learned, not just yesterday, but here I get 14 over 0 minus 1 plus 7. I think that's negative 14 plus 7. negative 14 plus 7. Now what we're trying to point out here is that you have to use the 7. But really what you're doing is you're just plugging in a 0 and trusting your math. Okay, but again, we can see that the 7 is affecting this answer. Maybe that's not a surprise to you. It's part of the equation, so it has to be part of these features. Again, check some stuff out. Did you type it in your calculator? Are you surprised by something? Or are you happy with what you've done? Again, the x-intercept is when you set the equation equal to 0. Now, yesterday, we didn't have an equation with this extra number, so we were able to just say, hey, what makes the numerator equal 0? But you got to understand this equation is more than just a numerator and denominator. Okay, it's got this 7, but if you kind of look at this equation, I feel like that it's just saying to you, use some algebra, solve for x. Okay, now if you subtract 7 from both sides, that would be a good algebra step. You kind of have yourself still looking at a denominator. We solved some more complicated fractions than this a couple weeks ago, but really you just got to take the denominator and multiply it to the other side. That's what you always do with a denominator when you're trying to solve an equation. Just multiply to the other side. Be sensitive to the negative 7. Distribute it. Get negative 21x plus 7. So you got yourself a little algebra equation. And after you subtract 7 and divide by negative 21, so we'll subtract 7 and divide by negative 21, we get 7 over negative 21, which happens to work out to be a little negative 1/3. Okay, but again, what I'm trying to show here is you can trust it. You can plug in 0, and more like set it equal to 0, and then solve for x. That's an x-intercept. Y equals 0. I kind of skipped the horizontal asymptote because I'm wondering if you guys checked it out or what you think about it. Yesterday's rules said that you should look at the numerator and denominator. You still should look at the numerator and denominator and conclude that the numerator is smaller than the denominator. When we say that, we mean the degree. The degree of the numerator is 0. The degree of the denominator is 1. So the numerator is smaller than the denominator. Do you remember what the conclusion is? Yesterday, it would have been 0. You would have concluded y equals 0. But if you look at the graph, you might be saying, that's not y equals 0. What do you see? How'd you do using the graph to kind of pull it all together? All right, 14 over the quantity 3x minus 1 plus 7. Okay, I know you haven't seen too many horizontal asymptotes, but it doesn't look like there's a horizontal asymptote right here. In fact, it looks like it's up here, up at 7, up there at 7. Okay, now what's happening here is also what has happened when anytime you add a number to an equation. I'm talking about like even back in sine and cosine land. What happens when you add a number to an equation? We call it a vertical shift. It happens with parabolas. It happens with rationals. It happens with any graph. So anything that can shift vertically will be affected by that plus 7. Hey, a horizontal asymptote, that's a perfect example of a line that can shift vertically. It's here at 0, boom, it pops up to 7. Now, what you want to realize is that it started at 0 based on the rules, but it shifted up 7, and now its final resting place is at y equals 7. The truth is, anything in this problem that can shift vertically was affected by that 7. Okay? The only thing that wasn't affected by it was the vertical asymptote. A vertical asymptote can only shift left and right. But anytime you have a number at the end of an equation, it will represent a vertical shift. Okay? And it will affect the x-intercept, the y-intercept, and maybe most notably, it affected the horizontal asymptote. I don't know if you have to take notes on that. Maybe you do want to say something. Most of us is just experience it and realize that now we can have a shift number. What do you think? Is there anything that you want to add to the cause here? Okay. Listen, the homework. There was a lot going on in there. I'd like to actually talk about a little bit more than just, hey, here's the answers. Because first of all, I don't have just all the answers, but what I've actually tried to do here is point out or pick out some really important stuff. There's a lot of information on here. It might be a screen that you want to take a picture of. Okay, that's not against the rules. What I'd like to actually do is verbally emphasize some things. It might be something that caught your attention. Maybe it's just good to listen to it. If there's something else that I didn't put up here, please, okay, ask. Just for example, number 11, horizontal asymptote. Don't be fooled by the order. Okay, the 2x is the degree, it's x to the first. The x is the degree, x to the first. So actually use the coefficients of 2x over x. The coefficients of 2x over x are 2 over 1. So you don't want to look at the 5 over 1, kind of don't be fooled by the order. Number 21, if you really got into it last night, you may have, for the first time, noticed that, wait a minute, it looks like that we're crossing a horizontal asymptote. Now, first of all, trust your math. 0, 0 is the intercept. That means it's a point, like a solid filled-in point. That means the graph is going to touch that point. In this case, it crossed the point. But what I'm getting at is it's not a hole in the graph. Sometimes people are like, oh, so you got an asymptote, now it's going to make a hole. Now, a hole is if you have a common factor, okay, which, by the way, happened in number 24 because you had a common factor of x plus 4. We're going to get back to that and really focus on it in a few days, but this is okay because horizontal asymptotes only apply to infinity. Where's infinity? Well, anything to the far left and far right. So I can cross a horizontal asymptote before I get to infinity. Now, number 24 did have a hole. It's a lot of times kids, that's what they sort of focus on. We're going to get back to that idea, but I'm still going to share that the hole is not the same as the x-intercept. In fact, what I really want you to realize is that there is no x-intercept. That's because x plus 4 kind of gets taken over by the other x plus 4. So the x plus 4 gives us negative 4, but it's already been kind of qualified or classified as a hole. Okay? So there's no number that makes the fraction equal 0. That's why there's no x-intercept. You get into the problems in the 40s. They should have kind of, again, caught your attention. I have to admit, I was a little bit fooled by number 41. What was I fooled by? The denominator. It looks like it should factor, but it's not factorable if you look at the combinations of numbers. Now, since you can't factor the denominator, what are you going to do? You should probably try to solve it with a quadratic formula. But if you do that, you get an imaginary root. Actually, you get a pair of imaginary roots. So the denominator it doesn't ever equal 0, even though it looks like it could or should. That means there's no vertical asymptote in number 41. If you graphed it, you would have clearly seen no vertical asymptote. Kind of the same thing with 42, vertical asymptote. The denominator can't equal 0. You have an even degree. There's no way x to the 4th plus 1 can ever go back to 0. So there's no vertical asymptote. There is a horizontal asymptote using the a over b. Okay, a over b is like 3 over 1. Now, obviously, as you go look at the graph, you realize that, yeah, there's no vertical asymptote, but there is this kind of interesting behavior as I go to infinity. That is that the graph snakes back down and gets close to the graph, and it also snakes up and gets close to the graph. Okay, we do have a y-intercept. You plug 0 in for x, and another example of crossing a horizontal asymptote. I know, we crossed an asymptote. Horizontal asymptotes can be crossed. Verticals cannot. Okay, verticals are a really solid wall. A horizontal asymptote only applies to infinity. Did you see something else last night and you were like, I want to ask about that? Are you sure? Okay, keep learning. Today is a lot of that. Like, we're going to continue to talk about the same things, but I'm also going to introduce to you something else. Before I just say what it is, let's kind of discover it through this problem. We're going to see if we can analyze let me get this kind of labeled here. Okay, we're going to see if we can analyze f of x equaling x squared over x minus 6. Kind of just looks like another little rational function. And one of the things I try to preach in math is we should be able to apply what we've learned before to something new. In fact, if I didn't tell you there was something new here, I would hope that you would kind of jump right in and you would say the vertical asymptote. I'll just abbreviate that VA. I hope you would say the vertical asymptote is -6. Check that, +6. Okay, that's definitely what makes the denominator equal 0. How about the horizontal asymptote? Okay, we have to think about those rules. Eventually you get those rules memorized because you realize that there's only like 3 situations. Here you should be concluding that the top is bigger than the bottom. The top is bigger than the bottom from yesterday's rules is none. Okay, no problem. Moving on to the y-intercept, you plug a 0 in for x. As I sometimes say, make sure that you are confident with the math. You don't have to show any work, but I'm showing it one more time that you basically end up with 0 over -6. That's a yes, you're allowed to do that. It actually comes out as 0. Now, if you plugged in 0 and you got 0, that means you have the point 0, 0. And as we said yesterday, that would be the same as the x-intercept. You might just want to double check something else about the x-intercept. Remember that's what makes the equation equal 0. Well, the only way that's going to happen, again, is if x equals 0. So we have the same point. Actually, it appears that this is kind of boring. All I got is this old vertical asymptote and basically an intercept. Well, as you're soon going to discover, that's not all that you have. And that's where the calculator comes in. Again, when you guys type these in, well, make sure the first time is not on a quiz. Okay, type them in, use parentheses. Now I'm going to change the window a little bit. If you want to change yours, it's fine. If you just want to watch up here right now, I'm going to change it to be from -30 to 50 for x and y. -30 to 50. Okay, I want to kind of pull out a little bit, zoom out, hoping that you guys will see something. Ready? Just by the way, it's a little bit of the math geek in me, but the calculator doesn't draw vertical asymptotes. It actually is not drawing it. It's not smart enough to do that. It's actually just doing what it's been programmed to do, connect dots. And it knows that there's a dot down here at the bottom, and it knows that there's a dot up here at the top. And it's just trying to connect them. It looks like a vertical asymptote, but that's not actually what's happening. Okay, sorry to sort of rain on your parade. What do you guys think? Do you see another asymptote? It's not the vertical one. I think we already see that. There's not a horizontal one. The rule says none. So what other asymptote could there be?
A diagonal.
A diagonal one. You mean like maybe that? Educated guesses on the equation of that asymptote? Now, as Brandon said, it's a diagonal line, so how do you write the equation, or what would an equation look like for a diagonal line? It would have to look like y equals mx plus b, right? Depends on how much of a mood you're in right now. Any guesses on the slope or y-intercept of that line? How about y equals x? That's kind of a fan favorite, y equals x. Okay. Not quite, right? Kind of seems close, though. How about y equals x plus 1? How about y equals x plus 2, 3? Y equals x plus 3. Y equals x plus 6. How'd you get that? Hey, it's all right. Actually, it's smart. I was wondering if anybody was going to look over here. It's got to have something to do with the equation. It turns out that that is correct. There is a slant asymptote. Okay, this is actually a new type of asymptote. There is a slant asymptote at y equals x plus 6. Now, a slant asymptote, bless you, it is kind of what it says. It's a slanted line that a graph is going to approach but never cross as we go to infinity. Okay, actually, slant asymptotes also are an infinity idea. Okay, so as I go further and further here to infinity, that means to the left. I'm going to get closer and closer to the slant, and that's also happening up here. Let's talk about a little bit more. Okay, yes, the answer is correct. Yes, it has something to do with the -6. It's not just as easy as saying, hey, it's the opposite, but it has something to do with it. You know, it's funny, we talk about fractions, but sometimes we forget that they actually are just a division problem. Okay, what if we do the division problem? What if we perform division? Now, what I'm really saying is that x squared is getting divided by x minus 6. And if x squared is getting divided by x minus 6, then we really only have one choice, but it's fine. It's called long division. Now you might want to get yourself a little bit set up for the long division. It doesn't hurt to get the placeholders in here. It also doesn't hurt to just say, have a good attitude. Okay, because long division is really how you divide a fraction, a rational function. Okay, I hope you're putting an x up here because x times x is x squared, and you always want this term to be the same. Of course, you continue to multiply, and you get a minus 6x. Now, be careful. This is still always the step that gets kids. You're subtracting right here. Subtracting. And when I teach this, I either show, okay, you're subtracting everything, or I prefer to distribute the subtraction sign. I prefer to say that means I'm going to change the sign. In the end, you get a 6x. In the end, you get a 6x, so that you can put a 6 up here. Okay, now, I should have brought down that 0. We end up with the remainder. The remainder is technically over the x minus 6. So I want you to think about something. Should it be, shoot. Should be plus. I want you to think about something. X squared divided by x minus 6 is equal to, listen carefully to this, x squared divided by x minus 6 is equal to x plus 6 plus this remainder. What I'm really saying is that what this fraction looks like graphically, what this fraction looks like is going to look like x plus 6. Wait a minute, x plus 6 is a diagonal line. Okay, it's going to look like x plus 6 plus this little remainder. That's why the graph starts to look like this slanted line. That's why it gets close to this slanted line. But it's like always getting pushed away. It's getting pushed away by this little remainder as you go to infinity. It's the same thing up here. Okay, the graph wants to look like the slant. That's because it equals x plus 6. But it always gets pushed away by that little remainder. Okay, that's the number theory. That's the number theory behind a slant asymptote. Okay, now what you're going to learn is that to find a slant asymptote, you only really kind of need two things. You need the degree of the numerator to be exactly 1 greater than the denominator. This is also a very important idea. You need the numerator to be exactly 1 greater. Now, when the numerator is 1 greater, the second thing you're going to do is you're going to realize that you just need to divide. Because whenever you divide, you will end up with a mx plus b. You'll end up with a y equals mx plus b. And that'll be your slant. Okay, we kind of say that you ignore the remainder. It's more like you realize that the remainder is what pushes you away from the slant. Because all you need is the mx plus b. Okay, so now I'll say we're looking for slants. Of course, now we have the potential to have a slant. Of course, not every problem has a slant, None of the ones on your homework last night had slants. If you would go back and look at them, you would quickly realize it's because the degree was not such that the top was 1 greater than the bottom. But now we see a problem like 3x squared minus 2x plus 1 all over x, where we quickly say the top is 1 greater than the bottom. And that's right, the top is 1 greater than the bottom. But back up with me a second. You still want to go through the analysis. Okay, in other words, you still want to think about the vertical asymptote. And then we'll go through the next and so forth. Okay, so what makes the denominator equal 0? That'll be the main idea for this whole chapter, but it's still true. It's still the vertical asymptote. The horizontal asymptote. Oh, that looks at the top and bottom also. Oh, wait a minute. We already figured out that the top was 1 greater than the bottom. That means, well, that always means you can't have both. You're not going to be able to have a horizontal and a slant. Okay, but we'll still note that. Now, there is a slant, and that means it's time to divide. Now, notice I didn't say you have to do long division. This is a perfect example of realizing, wait a minute, this numerator is just being divided by x. Okay, I hope you use the triple heart method. I hope you basically use simple division. Everything's being divided by x. We end up with 3x minus 2. Honestly, that's going to be your slant. But we also get a remainder. Just to note, we get a remainder, which is why y equals 3x minus 2 is able to be our slant. Again, you have to get a remainder to push the graph away from the slant. That's actually kind of interesting. Plug a 0 in for x. No. Can't plug a 0 in for x. You'll get a 0 in the denominator. Okay, so there's no y-intercept. Interesting comment about the x-intercept. Soon you guys are going to realize this. This is the first problem where I say it. Some x-intercepts cannot be found without a calculator. Listen, you can look for that x-intercept. You could use the quadratic formula, but I just want you to kind of relax a little bit and realize that, okay, I'm not going to make you run through all that all the time without a calculator. Now, it turns out that you get the square root of a negative number with the quadratic formula, which you can do, okay? Where you're like, wait a minute, I don't even know how to solve that. This one you could solve with quadratic formula, you just get a square root of a negative. All right, but you'll remember that in the future because it will happen. Okay, x equals 0, vertical asymptote. Now, when you graph your slants, think about slopes and y-intercepts. So that means, of course, my slant has to be down here at -2. And I do have a pretty steep slope. I guess I can kind of make my line look steep. It is just a sketch. Now, if you graph this on your calculator, you might find out that you don't see much. I'm going to skip showing it to you this time, but you guys have to explore a little bit. You might not see much. You might wonder where the branches are. Sometimes you have to zoom in. Sometimes you have to change the window. Sometimes it's just knowledge that tells you that there's going to be a branch somewhere on the left side. Now, it doesn't necessarily always have to be in this little corner. It doesn't have to be in this corner, although it is for this problem. And same thing up here. It doesn't have to be in this little wedge. It is, though, for this problem. In other words, there is the potential for a graph to be way out here. Okay. Not for this problem, though, but there is the potential for your branch to be kind of like on the outside. You'll see it. I can't show you everything in one problem. Okay, let me see what I want to do here. I'm well aware that we don't have unlimited time, but I feel like I want to at least expose you guys to what we can talk about with this equation. X cubed 2x squared minus 4x plus 2 all over x squared minus 4. It's clearly got a little more degree and it's got a little more denominator. You get into an equation, it's just got more. It's going to also have more variety on the graph. Make sure that you, though, are not missing those vertical asymptotes. Like this is a good example of when you take the square root of 4, make sure you get plus or minus. You can really mess up your graph by not realizing that there's 2 vertical asymptotes. Because you're going to learn the vertical asymptotes always divide up the spaces. They always divide up the intervals. All right, the top is 1 greater than the bottom. So, as maybe you're not surprised, there's going to be a slant, but no horizontal. Again, when you find the slant, you have to divide. And this type of problem, because the division is not just a single term, I can't use a heart method. I have to take the plunge and use long division. It doesn't take too many of these long division problems, though, to kind of catch on to the secret, which is that it's always going to be the beginning of the problem that produces your slant. Okay, because when I stick an x right here and gives me an x cubed minus 4x, I've already got the first term of my y equals mx plus b. And yes, I'm supposed to subtract right here. Yes, I'm supposed to do that. But what really matters is my next term. What really matters is looking at this x squared and this 2x squared and putting a 2 right here. Some of you might not be quite ready for this, but it doesn't hurt to hear it. You're done. That's y equals mx plus b. That's your slant. Should I finish the division problem? I could think about finishing it. All I'm really going to do is I'm going to think about the remainder that I get, but I've got my y equals mx plus b. Here's an old faithful. Plug a 0 into this equation. This is where I hope that the new stuff doesn't get in the way of the old ideas. Plug a 0 into the equation, you get 2 over negative 4. 2 over negative 4, of course, is negative 1/2. Most of the time, we kind of just do that mentally, I suppose, by just kind of looking at the equation. All right. I don't know. Do I have 30 seconds or a minute and 30 seconds? I just kind of want you to see the asymptotes. Okay, we have the vertical asymptotes, but I have that slant asymptote cutting through, and I'm going to stop short of being able to put this up on my calculator, but you get a branch in the middle, you get a branch in the middle, you get a branch on the left, here's one of these ones on the left, and then you get this one on the right. Obviously, you would have to take a little bit of time looking at your calculator to come up with that.